We deviate for a while from the main tracks of our story and discuss SURE, a technique for tuning parameters for the denoising algorithms. Here is our objective. We have a denoising algorithm, and our goal is to tune its free parameters so as to get the best possible performance. So if X is a clean image and V is the additive Gaussian noise, then the denoiser we have operates on Z and produces age of Z and theta. Theta is a vector of the parameters that controls this algorithm. We would like to choose theta such that the expected mean squared error between the ideal image X and the estimated one, age of Z, is minimized. We are about to present the idea that is summarized in this seminal paper by Stein from 1981. This is the Stein unbiased risk estimator SURE. Let's return to the error expression and expand it. All we did is to show each of the inner multiplications. Looking at these three parts, the first is relatively easy to handle because it is dependent only on the denoiser output. And the third is of no importance since it is not dependent on theta. The second term, however, seems like a dead end because it is dependent on the ideal image X, which we cannot have. We will take this second term and further analyze it, showing that there is a way to evaluate it even without having X. Let's use the relation X equals Z minus V and plug it into the problematic expression. This leads to these two terms. Again, the first is easy to handle, as both Z and the output of the denoiser are known. The second is impossible, as it calls for the knowledge of the noise vector. And so again, we take the problematic part and proceed our investigations with it. Writing the second problematic term specifically, it looks like this. Here we got a sum of ugly integrals which compute pieces of the expectation. Observe that we have used the fact that the noise is white and Gaussian. And here is another way to look at this very expression. The fact that Vk appeared outside of the exponent in the original expression suggests that we could present its multiplication by the Gaussian exponent as a derivative of this Gaussian. Does this remind you of anything? It should. It looks exactly like the kind of expression we see when integrating by parts. So let's use the formula for the integration by parts. Here it is, in its most general form. In our case, this leads to the following expression. The first term is evaluated on the borders, minus infinity and infinity. If we assume that the denoiser is bounded, this equals to 0 due to the Gaussian exponent. The second term is an integral that migrated the derivative to the denoiser. A convenient observation here is the fact that the derivative of h with respect to the noise V is the same as the derivative of h with respect to the input image Z. We are nearly done. Looking at the very last expression we got, it is nothing but an expectation of the derivative of the denoiser with respect to its input. Now we pack all the expression we have and get this equality. The error we so much want to evaluate is built of 4 pieces. The first is easy, as it is the norm of the denoiser output. The second is just as easy, being the inner product between the denoiser input and output. The third is a bit of a challenge, being the divergence of the denoiser, or in plain words, the sum of all its partial derivatives with respect to its input. The last part is a constant, which does not depend on theta and thus can be disregarded. One thing that kept popping out is the need to evaluate expectations. We cannot do that since we have only one realization of the noise. However, all the expressions we got accumulate their values by a summation over the entire image, and thus ergodicity replaces the need for a formal expectation. The bottom line is this. We have now a clear expression that gives an estimation of the mean squared error of the denoiser. Thus, by finding theta that brings this expression to minimum, we can tune the denoiser to get the best possible performance. Observe that a hidden assumption for all this to be true is the need for h to be differentiable. And that's it. This is the SURE.